Here we have another example of rotational motion. So we have a motor. It can provide a maximum torque. So this is a tau of 110 Newton meters. Assume that all of this torque is used to accelerate a solid uniform flywheel, which is a cylinder or disc. This flywheel has a mass of 10 kilograms and a radius of 3 meters. How long will it take for the flywheel to accelerate from rest to 6.5 radians per second? So how long? We're looking for a time. We're accelerating from rest. We have to specifically say omega, because whenever we're dealing with rotation, something that's going to rotate or is rotating, we have to use these angular quantities. Every point on this disc, this cylinder or flywheel, is going to have the same angular velocity at any given moment in time. So we're getting it up to a final angular speed of 6.58. All right, so torque related to motion takes us back to Newton's second law. The net torque on this flywheel will equal the moment of inertia of the flywheel times its angular acceleration. They've given us the torque. We can assume that is the net torque because there's no other forces mentioned. Moment of inertia, the first thing I would do is jump to the table, either within the e-text or on the test notes, and look for a solid uniform cylinder. I, for a solid uniform cylinder, is 1/2 mr squared. So since we have the torque, and we know m and r for this flywheel, we will be able to calculate this angular acceleration. Now we can continue symbolically if we want, or let's go ahead and just solve for alpha. The net torque is 110 Newton meters. Mass is 10 kilograms, R 3 meters. So alpha, the number, .44444. Those fours keep going all the way across my screen. Now, these units are radians per second squared. I want to show you that, though. So in the numerator, we have Newton times a meter. Newton being kilogram meters per second squared. We're multiplying that by meters. In the denominator, not 10, sorry, I want the units. Kilograms, and then meters squared. So the kilograms, these meters squared cancel, leaving us with 1/second squared. Those radians are implied. So I typically write them out. Technically, you could just write 1/second squared, and that's valid. But I always write out the radians when I know they need to be there, to know that I have made sure I have radians instead of something like revolutions or degrees in its place. So I'm going to go ahead, write out the radians per second squared. Now to finish this, we're trying to get to a time. We know this flywheel is starting at rest. We know it has a final angular speed of 6.58 radians per second. Now this torque is constant. I is constant. So this angular acceleration we've come up with is constant. Now the reason I'm pointing that out is because we have the set of kinematic equations that can be used when we know the angular acceleration is constant. So the big three, but for rotational motion specifically. So this is the one that has most of what I know. It's starting at rest, so omega initial is 0. Omega final we know. Alpha we now know. So we can solve for the time. I have 3 sig figs, so 2.69 seconds. Second cancels with one of those. That's what brings us the seconds up. And then both of them had radians in there. So this is how long it took.